Alright, now let us enter the next subtopic, which is called the thermodynamic processes. Okay, in this chapter, we have four essential thermodynamic processes that we need to understand. Okay, first one is called the isobaric process, and then the second one is called the isocoric or isovolumetric processes. This isocoric is also known as isovolumetric. Okay, isovolumetric. And then we have the third one is called the isothermal process, isothermal. And then the last one is called the adiabatic process. Okay, adiabatic. Okay, I shall begin with the first two, which is the isobaric and isocoric process. All right. So let us start with isobaric process. So what is the isobaric? What do you understand by isobaric? The word isobaric. Isobaric, iso, right? Let me write something. Iso itself means same or constant. Same or constant. Baric, bar. The word bar, what is mean bar? Bar is actually a unit of pressure. A unit of pressure. Do you heard about barometer? You heard about barometer before? Barometer is a instrument to measure the air pressure. Barometer is an instrument to measure the air pressure in certain environment. Okay, barometer. So bar, besides bar, is a unit for pressure. You know that one bar is actually 100,000 Pascal or 100 kilopascal. So bar is actually another unit for pressure. Actually, we have several units for pressure. We have bar. We also have atmospheric pressure, and we also have Pascal. Okay, we have bar, we have atmospheric pressure, we have Pascal. So bar is just another unit for pressure. So isobaric means constant pressure. Right? Let me write something. Look back to the notes. So isobaric means same pressure or constant pressure. Constant pressure is actually Charles' law. Constant pressure, because when pressure is constant, the only one changing is the volume and temperature. Pressure constant means only the volume and temperature changing. So for example, like if I heat up the gas, so the temperature will increase. Temperature will increase, so the volume of the gas also will increase. This is Charles' law. So V1 over T1 equal to V2 over T2. Charles' law. We use this PV graph to explain. So isobaric, constant pressure, means the graph is a horizontal line. Now, why horizontal? Because it has constant pressure. You see that? It has constant pressure. You see, from point 1, this is the condition 1. Point 1 is condition 1. And point 2 is condition 2. Point 1, it has volume 1, which is 10 meter cube. And also it has temperature 300 Kelvin. Okay, I put as T1. Volume 1, 10 meter cube. And then temperature 1, 300 Kelvin. And then point 2 has volume 2, which is 20 meter cube. And also temperature 2, 400 Kelvin. And these 2 points, 1 and 2, have the same pressure. That's why the line is horizontal, which is 100 Pascal. Pressure I put as P only. No subscript for P because pressure is constant. The volume and temperature has subscript. V1 and V2, T1 and T2, they have subscript because they are changing. So if you look carefully, when we heat up the gas, the temperature will increase. The temperature will increase, the volume also increase. Is it true? You see, when I heat up the gas, so the graph will go from 1 to 2. That means when I heat up the gas, the temperature will increase from 300 Kelvin to 400 Kelvin. Yeah, you see that? It jumped from a lower isotherm line to a higher isotherm line. The higher the isotherm line, the higher the temperature. Yeah, or we can say the further away the isotherm line from the x and y axis, the further away the isotherm line from the axis, the higher the temperature. So from 1 going to 2, the temperature actually increased from 300 Kelvin to 400 Kelvin. So as the temperature increased from 300 Kelvin to 400 Kelvin, the volume also increased. The volume expansion from 10 to 20. So that is Charles' law. When temperature increase, T1 to T2, volume also increase. When the temperature increased from 300 to 400 Kelvin, the volume also increased from 10 to 20. This is how we read, but the pressure is constant at 100. These values are just one assumption. Yeah, just one assumption. It can be any value. Okay. Remember that in this chapter, the temperature need to be in Kelvin. Yeah. As you learned in previous chapter, kinetic theory of gas, you using Charles' law. Yeah. This Charles' law actually comes from the formula PV equal to nRT. So this temperature they all consider a single temperature point. Single temperature. So this temperature all need to be in Kelvin. So cannot degrees Celsius. If your question gives you the temperature in degrees Celsius, you need to change to Kelvin. Yeah, remember that. Need to change to Kelvin. Okay, that's about the Charles' law. Now, how about let's talk about work done first. Yeah, let's talk about work done. What is actually work done? Work done is area under the work done is actually how we get the area work done. Work done is actually area under the pressure volume graph, the PV graph. Work done is the area under PV graph. So as you can see, this one, the orange area, this is the work done of the gas. Okay. So this is a rectangular shape. How do we get the rectangular shape? So this is how we get the area. Yeah. So pressure times change of volume. Is it true? Is this the formula for the rectangle? Yes. Yeah. So pressure. This is the pressure. Okay. This is the pressure, or the height. And change of volume is that means V2 minus V1, or final volume minus initial volume. Final volume minus initial volume, you get the length of the rectangle. Okay, you get the length and the height. You see that? So pressure. This is the maybe I should write something here. So this is the pressure, and this is the change in volume. Change in volume is the V2 minus V1. Okay. So this area rectangle is the work done. So for isobaric process, very easy to find the work done because it's just a rectangular shape. Okay, that's the work done. Now, let's look at the first law of thermodynamics. Yeah, the equation of first law of thermodynamics. Now, about the delta U. Delta U is the change in internal energy. Is there any change in internal energy happening? Is there any change in internal energy of the gas? Yes. This isobaric process or Charles' law, yeah, isobaric process is a Charles' law process. It involves change in internal energy. Why we say involve change in internal energy? Because got change in temperature. You see that? From T1 going to T2. You see, from T1 going to T2, there is a change in temperature. When there is a change in temperature, there is change in internal energy. Because why? Because internal energy depends on temperature. Internal energy of gas is F over 2 NKT. F over 2 NKT. So that means when the temperature changes, the internal energy also changes. You see that? Because temperature is not constant. For this Charles' law, temperature is not constant. The temperature changes from T1 to T2. So the internal energy also have U1 and U2. That means there is change of internal energy. Okay, so in change of internal energy, the delta U is not zero. Yeah, it's not equal to zero. And just now we also have learned the work done is not zero also because work done is a rectangular shape. The pressure times delta V. So delta U is not zero, work done is not zero, so Q also not zero. The heat flow also not zero. So all these three not zero. Yeah, all these three not zero. Okay, not zero. So they don't have any zeros. Yeah, Q is not zero, delta U not zero, W also not zero. So we can predict like this. Heat flow? Let's talk about heat flow. Heat flow, maybe heat is absorbed. Okay, maybe heat is absorbed. Okay, maybe heat is absorbed, go into the gas. Yeah, heat energy from the surrounding absorbed into the gas. So what happened to the internal energy? When heat is absorbed into the gas, the internal energy may increase. So the temperature maybe increase from T1 to T2. Besides that, the gas also can do work. Maybe expansion, work done positive. So maybe the gas also can push the piston up. All right. Or maybe someone compress on the gas. Work done is negative when work done on the gas, compress the gas. Work done negative, compress the gas. So this process involve all these three. Got Q, got delta U, got W. Okay, that is isobaric process. All right, that is isobaric process. So isobaric, very simple. Just constant pressure. The line is horizontal line, yeah, because it maintained at constant pressure. So the volume and the temperature will change. Okay. Now let us look at the following one, which is the isocoric process. Okay, isocoric process. Isocoric process has another name. It's also called isovolumetric. Maybe the isovolumetric explains more about the meaning. So you can straight away see iso, same volume. Isovolumetric means same volume. So that means for this process, the volume is constant. Volume is constant. Isocoric process means volume constant. So if volume constant, so if volume is constant, so the pressure and temperature will change. The pressure and temperature will change. So this is the pressure law. So we have P1 over T1 equal to P2 over T2. So that means when temperature increase, temperature of the gas increase, the pressure will increase also. Yeah. Let us look at the graph. Yeah. Let us look at the graph, the PV graph. For example, this isocoric process. Isocoric process means the volume is constant. So when volume constant, it maintain at the same volume of same value of volume. It maintain at the same value of volume means the graph is a vertical graph. Just now isobaric process is a horizontal graph maintained at constant pressure, but isocoric process maintained at constant volume. So it become a vertical graph. If vertical graph like this, there's no area, isn't it? If you look directly, if the graph is vertical, there's no area under the graph. So if no area under the PV graph, of course work done is zero. Yeah, work done is zero. No work done. For isocoric process, there's no work done. Yeah, no expansion, no compression. Okay, we will talk about that later. Okay. look at this graph. It's a vertical graph. It maintains a constant volume. So this is 0.1, this is 0.2. Actually, the graph can go up or can go down. If go up, means the temperature increase. If the graph go up, the temperature increase from 300 to 400. If the graph go down, means it's a temperature decrease, or the 400 Kelvin becoming 300 Kelvin. Okay, so if the graph go up, means the gas become hotter. If the graph go down, means the graph become colder. Do you see that? Okay, maybe I should write something. Is even the isobaric process, going to the right is getting hotter, yeah, because it jumped from 300 Kelvin to 400 Kelvin. If going to the left, is jump from 400 Kelvin to 300 Kelvin. So this one is becoming colder. You see that? Going to the right become hotter, going to the left become colder. For isocoric process, going up is becoming hotter, because from 300 Kelvin going to 400 Kelvin is becoming hotter. But if going down, if the graph going down, is actually become colder. The temperature decrease. The temperature decrease from 400 Kelvin to 300 Kelvin, becoming colder. Okay. So you see that. You see, yeah. Let's talk about only the first graph. Okay. So from point 1 going to point 2, point 1 it has point 1 and point 2, they have the same volume. 10 meter cube. Okay. But point 1, it has the pressure 100 Pascal, and point 1 also have temperature 300 Kelvin. Point 2, it has higher pressure 200 Pascal, and it also has a higher temperature 400 Kelvin. Temperature 400 Kelvin. So for isocoric process, when you heat up the gas, the temperature increase. The temperature increase, when you heat up the gas from point 1 to point 2, the temperature increase from T1 to T2, from 300 Kelvin go to 400 Kelvin, the temperature increase. The pressure also increase. Do you see that? The pressure and the temperature, they are proportional. When temperature increase from 300 Kelvin to 400 Kelvin, the pressure also increase from 100 to 200 Pascal. So going up is becoming hotter, going down is becoming colder. Okay, that's isocoric process. Okay, so it's a pressure law. Isocoric is a pressure law. Now, just now I said when the graph is vertical, it has no area under the PV graph. No area under PV graph means no work done. Zero work done. So for the first law of thermodynamics, Q equal to delta U plus W, we can cancel out the work done because work done is zero. For this isocoric process, the work done is zero. So work done is zero, so Q is only equal to delta U. We can imagine the system is like this. When there's no work done, when there's zero work done, means, what means by zero work done? Zero work done means there's no work done by the gas or no work done on the gas. That means there's no expansion and or no compression. The volume is always constant because the volume is constant. You see that? The volume is constant, no expansion, no compression. Okay? So work done is zero, no expansion. The volume does not increase or does not decrease because the volume is always constant. Okay. So it's just like the piston is get fixed by, you see a nail there? The piston cannot move up, cannot move down. The piston cannot move up for expansion. The piston also cannot be compressed. The piston cannot move down to compress the gas. So no expansion, no compression. Yeah? The volume is fixed. The volume is constant. Okay. Isocoric process is work done zero. So what happened in this process is Q equal to delta U only. So work done is 0. So we only have Q and delta U. So that means if Q is positive, delta U also positive. If Q is positive, delta U is positive. If Q is negative, delta U is also negative. What does it mean by this? Okay, Q is positive means heat absorbed, isn't it? Q positive means heat absorbed. We can imagine like this. It's just like if Q positive, that means the heat enter. When Q positive, heat enter. So when Q positive, heat absorb, enter into the gas. The heat energy enter into the gas. So where the heat energy goes? It's stored in the form of internal energy. So when the heat energy is absorbed into the gas, the internal energy of gas will increase. The internal energy of gas will increase. So delta U is positive. Delta U is positive means internal energy increase. When internal energy increase, temperature of the gas increase. Okay, temperature of the gas increase. So based on this formula, when the internal energy increase, the temperature increase. See that? This formula, when the internal energy increase. Why the internal energy increase? Because heat is absorbed into the gas. Heat is absorbed into the gas, and the gas cannot do any work because the volume is fixed already. So this heat energy just stored inside the gas. So the internal energy increase. So what happens is the temperature of the gas will also increase. Temperature will increase from T1 to T2. You see that? Become hotter and hotter. Hotter and hotter. Also, and also another thing is the root mean square speed also will increase. When internal energy increase, temperature increase, the root mean square speed of the gas particle inside also will increase. The gas particle inside the gas also will move faster. The gas molecule will move faster inside the gas. Okay, that's the first one. The second one, Q negative. When Q is negative, delta U is also negative. What does it mean by this? Let me look at this. Okay. Now, when Q negative means heat is released. Heat is released. That means heat energy is lost. Heat energy is lost. When heat energy lost, so when heat energy lost from the gas, what happened to the internal energy? The heat is lost from the gas. So of course, the internal energy of the gas will decrease because energy loss. Energy loss from gas in the form of heat. Yeah. So the internal energy of the gas will also decrease. When that Q negative, heat energy loss from the gas, so the internal energy of the gas will decrease. Delta U negative, internal energy of the gas decrease. The temperature of the gas will also decrease, getting colder. The gas getting colder. All right. This is what it means by conservation of energy. The energy is not being destroyed. Yeah, it must go somewhere else. It must store in somewhere else. Yeah, cannot just disappear like that energy. Yeah, this is conservation energy. The heat energy, when the heat energy goes in, it doesn't just disappear like that. It will store inside the gas in the form of internal energy. When the heat energy is lost, the internal energy of the gas will also decrease. It's all about conservation energy. So first law of thermodynamics is all about conservation of energy. Okay, so that's about it for isobaric and isocoric process. So very simple. Isobaric means constant pressure. When constant pressure, the graph is horizontal. Graph is horizontal. You have a rectangular shape work done. Just get the area of the rectangle. You get the work done. Okay, and it has all values. You have Q, it has delta U, it has work done. Okay, for isocoric process, it's a constant volume. Constant volume means no expansion or no compression can happen. No expansion or no compression can happen. No work done by the gas, no work done on the gas. So work done is 0. Yeah. Or if you look at the graph, also it is a vertical graph. Yeah, going up. And just now it's horizontal. This is vertical. When vertical graph, there's no area under the graph. Of course, no area, no work done. Okay, and work done is 0. So you only have Q and delta U for isocoric process. Okay, that's the first two thermodynamic process. So let us go on to the next two process, which is called the isothermal process and adiabatic process. Okay, thank you.